Hi, you are at level 6 out of 30 easy steps to learn everything of Einstein's theory on special relativity. Have you always been curious about what it is all about, but feared its math or its complexity? Then these levels are for you. And today we are going to meet a true rock star on Einstein's mountain, Coulomb. GP, hit it! Today we are going to talk about Coulomb. He did some experiments and found a formula for the electrostatic force. It's one of the many pieces of Einstein's puzzle, and we will look in detail about what it is all about. If you're new to the story, my name is Tom and I'm on a mission. My mission is to get everyone on top of Einstein's mountain in 30 easy steps accessible for everyone regardless your educational background. So if you want to know more about these levels, you can see my introduction at level number 1. But now let's talk Coulomb. Charles-Augustin de Coulomb. Who was this rock star? Here he is, painted. He lived from 1736 until 1806. And I looked at several lists online to find out if he is ranked among the greatest scientists or greatest mathematicians. He was not. But he made a very, very important step, a very important piece of Einstein's puzzle. We are going to talk about it. He's French, and he discovered something that we now call Coulombs Law. It's a description of the electrostatic force of attraction and repulsion. I'm sorry, I had to cough. It's an experimental law. He did experiments and then wrote down his results in a table, made a graph, made a model, as we've seen with the happiness formula or when we lost weight. So where are we on the timeline? I like to give you a feel of where we are in the timeline. So if we look at Einstein, you know, the top of the mountain, that will be in 1905. And today we are at 1785. And we discussed Galileo Galilei before, and he was from 1632 when he discussed the principle of relativity. Newton is on the timeline. Why? Well, Newton is not really a big part in this story, but you know, he's the greatest. So no matter what the timeline is, you put Newton on it. It could be a timeline of the history of tennis, and you just put in 1687, Newton published his Principia. And that's what we do. That's in honor of the greatest of all. So, enough jokes. Let's continue. So, Coulomb's law, what is it? Coulomb's law tries to, it quantifies the force between two electrically charged particles. Let me get my experimental test charges here. So here they are. If they are both positively charged, they want to get away from each other. They don't like each other. If they're both negatively charged, they also want to get away from each other. But if one is positive and the other is negative, then opposites attract. Boom! They want to meet. And the force between them is always pointing towards the, so they're eyeballing each other all the time. It's like a staring competition. So let's dive in a little bit more. The electric force at rest, we call it the electrostatic force, or sometimes to honor Coulomb, the Coulomb force. And you know this force. If you have a balloon and you rub it on your sweater, it gets charged. I'm not sure if it's positive or negative, but it gets charged. And your hair is also has some charge, probably. And when you move the balloon to your hair, the electrostatic force tries to pull the hairs to the balloon. So that's what happens. And Coulomb, he knew this phenomena, and he wanted to know how much force. What are the variables making up this force? So here we have an experiment. I have two charged particles. The red one has a charge of 10 coulombs. We will look at Coulomb in a moment. Plus 10, positively charged. And there's another charge, and it's negatively, has a negative charge, minus 5 Coulomb. So Q1 plus 10, charge number 2, Q2, has a charge of minus 5. And they are set apart by some distance, r. And they want to meet. They pull each other. And the force that the blue one is pulling on the red one is exactly the same as the force the red one is pulling on the blue one, only they are in different directions. If they would have been both positively charged, the forces would go outward. And also if they were both negatively charged, outward. But if one is positive and one is negative, opposites attract. They want to meet. So there you go. And what he did is, well, let me try to vary the distance between the particles. Let me try to vary the charge, plus 10, plus 20, whatever, and just make a table and see how the force changes when I change the charges or when I change the distances. And he found out this equation. The force has a magnitude that is some constant, we will look at the constant in a while, multiplied by the charge of particle 1, multiplied by the charge of particle number 2, divided by this, do you call it square? The square, not the square root, but the, times r times r squared, the distance squared. So, what does this say, this formula? Just look at it. Suppose you would double the charge of Q1, then the force doubles. If you would double the charge of Q2, the force doubles. And if you double the distance between the two particles, the force doesn't double. No, it gets weaker. The further they are apart, the less the attraction. And it's squared. So if you double the distance between the two particles, the force will be divided by 4. 4 times less whenever you double the distance. So it's not linear. Yeah. So in the beginning, when they're really tight, the force is almost infinitive. You know, it's huge. And when it goes, when they are not together, then the forces go weak, and very soon they are almost close to zero. So that is the nature of the electrostatic force. Later, they changed the formula. The constant, K, they replaced it with an epsilon, but not just with an epsilon, no, they divided 1 by the epsilon, and they put in 4 pi. And I ask myself the question, why? And the answer is, mathematicians are evil. We've talked about evil mathematicians in previous levels many times. Again, evilness here. They want to make things more complex. So we can't understand their secrets. But, it's really it's not that easy. It is easy, I would say, to go from one to the other. Then why pi? I guess mathematicians have some kind of fetish for pi. So if they see a formula which doesn't have pi in it, they want to change the formula. And that's what they did. Not with 1 pi, but with 4 pi's to make sure pi is really in there. And that's two ways of writing down the same law of Coulomb. So here it is again. R is the distance between the two charges, the two particles. Q is the charge in Coulomb. It has some unit of measurement. How do you measure charge? Well, in Coulomb, because he was the first to do experiments on this, so he got the honor of having the unit of measurement for charge named after him. So here it is. And very recently, well, depending on when you are watching this story, but I'm taping this in May 2020. So 1 year ago, the Coulomb has been defined, well, redefined, exactly as being one proton. You know, when you, well, we didn't talk about electrons and protons, you know, it's chemistry. I'm assuming you know what protons and electrons are. If there are more protons than electrons, something has a positive charge. If there are more electrons than protons, something has a negative charge, right? So let's take one proton and listen how much charge it has. It has 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000It's called the elementary positive charge E. Well, it will become clear why this number came up. So if you want to have 1 Coulomb, a particle with a charge of 1 Coulomb, you need a whole lot of protons. I'm not going to repeat the number here, but here you see the number of protons you would need in a single particle to get a charge of 1 Coulomb. And there it is. But this makes a little bit more sense. If charges are moving, and that's what we call a current, they are moving through a wire, and let's say the movement has a strength of, well, the current has a strength of 1 ampere, which is a different unit of measurement. It's a measurement of moving particles or charges. If you would have a wire which had a steady current of 1 ampere, and you would look at it for 1 second, then exactly 1 Coulomb of charge would have been moved, would have passed a certain point. And that means 6, 2, 4, 1, etc. protons went through that wire at any point. So, what about this constant? Well, the thing is, you know, in physics, if you make up laws like this, then all the variables have some unit of measurement. So if I do it in meters, I get different numbers when I do it in miles. If I do it in hours, I get different numbers when I do it in seconds. So you always need some constant to make up for the units you have chosen. And in this case, force has a unit of Newton, the greatest of all. Q has the unit of measurement Coulomb. R, the distance, has the unit of measurement meter. And then you need some constant, and it's called the Coulomb constant, to make the numbers work. And yes, they defined this constant because they defined the Coulomb in the equation. And well, meters has been defined, newtons have been defined, so then they could define how big K should be. And here it is, 8.98, etc., multiplied by a 1 with 9 zeros. And its unit of measurement, you can forget about this of course, Newton meter squared per Coulomb squared. Then the other equation where they introduced the epsilon. It's the electric constant. It has many different names. A little bit of evilness from the gracious physicists, right? Not always the mathematicians are evil. Here the physicists are evil. They just can't make up their mind how to call this constant. So it has many names. And if you try to understand what it means, I found this really difficult, but it's something like the capability of vacuum to permit electric field lines. Well, we'll learn about electric field lines in about 28 years. So again, 1 year ago, they defined the electric constant. Well, we know the formula. We know that the electric constant is the same as 1 divided by the Coulomb constant multiplied by 4 times pi. So you can do this on your calculator. Multiply the Coulomb constant with pi n times 4 and then divide 1 with that number and you will get 8.85 etc. multiplied by 10 to the power minus 12. So it's 0.000000001. And its unit of measurement is farad per meter. You can forget about the units here. So this is about constants, and sometimes these constants are revised. In this case, they have been exactly defined. 2 of them, the first one, the charge and the Coulomb, and the electric constant is just a formula. These unit of measurements, they all are part of what we call the system international system, System International, SY. Here you see a room full of probably, I guess, the brightest people of all, mathematicians, scientists, physicists, etc. And this is in 2018 where they proposed to change some of these constants. And if you want to know how such a session goes, I've put in the URL, it's there, and you can watch it for 2 hours, 24 minutes and 21 seconds if you want to. No, seriously, I mean, it's serious. So let's look at the law one more time. As said, it's depending on the strength of the charges and the distance between them. So if the charges go like this, the charges just move along. They want to keep looking at each other. It's the staring contest. So wait a minute. It's a vector. Yes, the force is a vector. And if you look at the formula, the equation there, it's not a vector. There are no on top of anything, but there should be. So if you want to know more about vectors, you can look at level number 3. But this is the formula in vector notation. Twice, one with the k and one with the epsilon. And here it says the force being at Q1. Let's read it. The first part of the equation. The force at Q1 vector equals the same force acting on Q2 but with a different direction, and it's defined by, again, K times Q1 Q2, and then we have to divide by the square of the distance, but we need to get a vector as well. So what we do is, first we get the length of the vector, and mathematicians do this with vertical lines in the beginning and the end. That means the length of the vector. So it's not a vector anymore, that's just a number, a scalar. So if you have a vector that has a length of 3, you do and you get 3. So we divide Q1 and Q2 by 3 squared, which is exactly the same as the formula we saw in the upper right corner. Now how do we make it a vector? Well, we need direction. We now know the length of the vector that we want, namely k times Q1 Q2 divided by r squared. But now we need to direct the force. So, well, we can look at the vector r that goes from Q2 to Q1. That's a vector. You can draw a arrow from Q2, the middle of Q2, to the middle of Q1. That vector has a length, the length of r, and if you divide it by its length, r, you get a vector with just a length of 1, but it has the correct direction we were looking for. So together, you know, isolating the length and isolating the direction, together you get the vector F, the force vector. And that's why I should have drawn in the second image arrows on top of the F for force. If you find this difficult, it's okay, you know, you can forget about it. If you know that the force will always be acting on the charges, and the direction of this force is always, they're always looking at each other, or they're always facing, doing quite the opposite, you're good to go. You know, that's more than enough on this mountain of Einstein. So, you've made it to the end of this level. You have revealed another very important piece of the puzzle on Einstein's mountain. You've met another rock star who did what scientists do: experiment, make a table, make a graph, make a model, have some constants, have some unit of measurements, make sure you get the honor and they name it after you, etc. And here it is. Thank you again, and I hope to see you at the next level. GP, hit it!